Mysterious electronic music plays softly in background. What if I told you that reality, the very fabric of existence that you perceive with such certainty, may be fundamentally different from what you believe? What if the universe as we understand it is merely a shadow, a projection, or one of countless parallel realities spawning with every passing moment? Welcome to Lecture 50 of our Unusual Science series, where today we delve into the enigmatic realm of bizarre theories in physics. I'm your guide through this labyrinth of mind-bending, concepts that challenge our most basic assumptions about reality. Physics stands at the precipice of knowledge, peering into the abyss of the unknown. And at this boundary, strange theories emerge, not from the minds of eccentric outsiders, but from respected scientists wrestling with the profound mysteries revealed by our most precise measurements and mathematical models. What makes these theories so bizarre isn't their lack of scientific rigor, but rather how dramatically they depart from our intuitive understanding of reality. They are the offspring of solid mathematics and experimental puzzles, yet their implications seem to border on the philosophical, even the mystical. Today, we'll explore 5 of the most perplexing theories in modern physics. The multiple worlds theory, which suggests that every quantum possibility manifests in its own universe simulation theory, proposing that our reality is merely an advanced computer program. The holographic universe, which argues our three-dimensional reality emerges from information encoded on a distant two-dimensional surface. The bizarre concept of Boltzmann brains, conscious entities arising spontaneously from random fluctuations in space, and the one-electron universe hypothesis, which suggests that all electrons in existence might actually be the same particle. Each of these theories emerges from rigorous physics, yet each leads to conclusions that seem to shatter our perception of reality itself. Let us begin with perhaps the most vertigo-inducing of all, the multiple worlds theory, also known as the many worlds interpretation of quantum mechanics. Proposed by physicist Hugh Everett III in 1957, this theory attempts to resolve the paradoxes of quantum mechanics without sacrificing mathematical consistency. The central premise is as breathtaking as it is disturbing. Every time a quantum event occurs with multiple possible outcomes, reality itself branches, creating separate universes for each possibility. Consider Schrödinger's famous cat thought experiment, where a cat in a box is simultaneously alive and dead until observed. In the many worlds interpretation, both outcomes actually occur, but in separate universes. One universe contains an observer finding a living cat, while in another, a parallel version of the observer discovers a dead one. This isn't just philosophical speculation. It emerges directly from the mathematics of the Schrödinger equation, taken at face value without the additional postulate of wave function collapse. While other interpretations add rules to explain why we only observe one outcome, many worlds simply says, all outcomes happen, just in different branches of an ever-expanding multiverse. The implications are staggering. At this very moment, countless versions of you are experiencing every possible variation of this lecture. In some, you stopped watching minutes ago. In others, the content differs slightly. In yet others, you're watching a completely different topic. What's particularly unsettling is that this theory has never been experimentally disproven. In fact, it remains one of the most mathematically consistent interpretations of quantum mechanics. The primary objection isn't its scientific validity, but rather our psychological resistance to such a profoundly unintuitive view of reality. Moving from quantum perplexities to computational conundrums, we encounter another disorienting possibility: simulation theory. What if the world as we know it, the stars, the planets, the quantum fields, and even our consciousness, is merely an elaborate simulation running on an incomprehensibly powerful computer? This theory, popularized by philosopher Nick Bostrom and endorsed by figures like Elon Musk, suggests that what we perceive as physical reality may be nothing more than sophisticated code. The argument is deceptively logical. Consider our own technological trajectory, from Pong to photorealistic virtual environments in just a few decades. If technological advancement continues, creating simulated minds within simulated worlds would eventually become possible. If advanced civilizations could create such simulations, and create many of them, then simulated minds would vastly outnumber real ones in the universe. Statistically speaking, the probability that we are among the original biological beings, rather than the much more numerous simulated beings, becomes vanishingly small. Some physicists have suggested that certain features of our universe hint at a simulated nature. The existence of a smallest possible unit of space, the Planck length, the cosmic speed limit of light, and even the bizarre behaviors in quantum mechanics could be interpreted as processing limitations or optimizations in the program that runs our reality. Scientists have even proposed experiments that might detect the computational nature of spacetime, searching for artifacts like pixelation or computational shortcuts at the smallest scales. While no conclusive evidence has emerged, the possibility remains tantalizingly open. Let's now traverse to perhaps the most mathematically robust of our bizarre theories, the holographic principle, which suggests our three-dimensional reality may be encoded on a distant two-dimensional surface, much like a hologram. This theory didn't emerge from speculation, but from serious work on black hole thermodynamics by physicists Leonard Susskind and Gerard 't Hooft. They discovered that the information content of any region of space appears to be limited not by its volume, but by the area of its boundary, a deeply counterintuitive finding. The mathematics suggests that all the information that makes up our three-dimensional reality, every particle, force, and quantum field, could be completely encoded on a distant two-dimensional surface, similar to how a holographic film contains all the information needed to project a 3D image. This isn't merely philosophical. It has found application in advanced theoretical physics, particularly in string theory and quantum gravity research. The AD-SCFT correspondence, a significant breakthrough in theoretical physics, provides a mathematical framework that supports this holographic view of reality. Evidence for this bizarre possibility comes from unexpected places. Some cosmological observations match predictions made using holographic models. Calculations about quantum entanglement make more sense in a holographic framework. Even the behavior of certain quantum systems, like quark-gluon plasmas, can be modeled using holographic principles. If true, the implications are profound. Space itself, the three-dimensional expanse we navigate daily, would be an emergent phenomenon, a projection of more fundamental information stored on a boundary that might exist at the edge of our universe, or perhaps even in a different dimensionality altogether. Now we venture into even stranger territory with the concept of Boltzmann brains, perhaps the most unsettling theory we'll discuss today. Named after physicist Ludwig Boltzmann, this concept emerges from thermodynamics and the study of entropy. In an infinitely old universe, random fluctuations in the arrangement of matter and energy would occasionally, incredibly rarely, but inevitably, create ordered systems. Given enough time, these fluctuations could theoretically produce fully functioning, self-aware brains, complete with false memories and the illusion of existing in a world like ours. The disturbing paradox is this. In an eternal universe, these spontaneously forming conscious entities would vastly outnumber consciousnesses that evolved through conventional means. Statistically speaking, it would be far more likely for a single brain with false memories to appear from random fluctuations than for an entire ordered universe with evolutionary processes to exist. This leads to an unsettling question. How can we be certain that we aren't Boltzmann brains, isolated consciousnesses floating in void, hallucinating an ordered reality that doesn't actually exist? Cosmologists take this problem seriously enough that they use it as a constraint on universe models. Any viable theory of cosmic evolution should explain why we observe an ordered universe rather than being isolated consciousness hallucinating order in chaos. The leading resolution involves cosmological inflation and the finite age of our universe, conditions that make traditionally evolved consciousness like ours more likely than Boltzmann brains. Still, the mere plausibility of such entities from established physics principles is enough to induce existential vertigo. Our final theory today is perhaps the most elegantly bizarre, the one-electron universe hypothesis, first proposed by John Wheeler to Richard Feynman in the 1940s. The essence of this idea is both simple and profound. What if all electrons in the universe, every single one of the seemingly countless identical particles, are actually just one electron, zigzagging back and forth through time. Wheeler noted that an electron traveling backward in time would be indistinguishable from its antiparticle, the positron, moving forward in time. He proposed that the single electron's world line could weave an incomprehensibly complex path through spacetime, appearing to us as countless particles. This would neatly explain why all electrons appear perfectly identical. They literally are the same particle at different points in its extraordinarily complex journey through time. It also explains the observed balance between electrons and positrons in pair production and annihilation. While modern quantum field theory has superseded this specific model, the core insight, that particles and antiparticles can be viewed as the same entity moving in different temporal directions, remains valid in our current understanding of quantum electrodynamics. The one-electron universe serves as a reminder that in physics, the most elegant explanations sometimes involve reconceptualizing our fundamental notions of time, identity, and causality, rather than adding new entities or forces to our models. As we survey these 5 bizarre theories, certain patterns emerge. Each challenges our intuitive understanding of reality. Each emerges not from wild speculation, but from serious attempts to resolve inconsistencies in our observations or mathematical models. And each carries profound philosophical implications about the nature of existence. Whether reality branches endlessly, projects holographically, runs as a simulation, allows for spontaneous consciousness, or contains particles looping through time. These possibilities remind us that the universe may be far stranger than our evolved intuitions can comfortably grasp. These theories also demonstrate why physics continues to advance, by being willing to follow the mathematics and evidence wherever they lead, even into realms that seem impossibly bizarre. As Niels Bohr reportedly told a colleague, "Your theory is crazy, but it's not crazy enough to be true." The history of physics teaches us that today's bizarre theory often becomes tomorrow's established framework. After all, quantum mechanics and relativity once seemed utterly absurd, yet they now form the bedrock of modern physics. This willingness to entertain strange possibilities, while maintaining rigorous standards of evidence and mathematical consistency, is what distinguishes good science from mere speculation. The theories we've explored today all make testable predictions, even if current technology limits our ability to perform definitive experiments. As our experimental methods advance, some of these bizarre possibilities may be ruled out, while others might find supporting evidence. What's certain is that physics will continue to challenge our conception of reality, revealing a universe more strange and wonderful than we can imagine. I leave you with this thought. Perhaps the most bizarre aspect of these theories isn't that they might be true, but that even if they are, we continue our lives unchanged, navigating a world that feels solid and singular, even if it's actually a holographic projection of information stored elsewhere. One branch of an infinite multiverse, a sophisticated computer simulation, or the creation of a single particle's dance through time. In our next lecture, we'll explore the philosophical implications of modern science, examining how discoveries in physics, cosmology, and neuroscience are reshaping our understanding of consciousness, free will, and the nature of reality itself. Until then, remember that in the pursuit of scientific truth, the universe rarely conforms to our expectations, and that's precisely what makes it so captivating. Mysterious electronic music fades in as credits appear.